Okay, in chapter 12, we're going to start talking about mechanical waves and sound, and how a mechanical wave produces sound. So the goals for chapter 12 will describe mechanical waves, what they are, how they work, mathematical formulations of them. We'll also study superposition, which is just putting one wave on top of another and then seeing how these waves interact. We'll talk about standing waves, special type of kind of superpositioning waves together, and we'll also talk about sound. We'll present sound as a longitudinal wave, so we'll sort of talk about what sort of a wave sound is. We'll talk about interference between waves as well. So we'll talk about constructive interference and destructive interference, which is basically how waves interact when we put them together. We can put 2, 3, 4, as many waves as we want together, and we'll see how they interact. We'll also talk about sound intensity, and we'll define beats, and we'll also talk about the Doppler effect. And briefly at the end, we'll talk about some applications of acoustics and waves and musical tones a little bit. But the coverage for the chapter is pretty much the whole thing, 12.1 through 12.12. So what is a wave in its broadest sense? I'll just read this off the slide here. Waves occur in all branches of physical and biological sciences, and is one of the most unifying concepts running through all the natural sciences. It's very relevant to a multitude of physical and biological applications. We really find waves everywhere. So it's very, very relevant to a lot of things. Now, very broad sense of what a wave is that anytime you have a system that's in equilibrium, and then you disturb it at one of its ends, then that disturbance can travel throughout the entire system. So we say that disturbance can propagate from one region of the system to another region of it. So essentially, you just have a disturbance somewhere that travels throughout, just like you have the ripples on this pond right here, or pool or whatever it is. You have a disturbance at this point right here, and this disturbance is transmitted all out in all directions around the edges, right? So these are all waves. It's a transmission of that disturbance. And we'll see later on that it's really just a transmission of the energy from one point to another. So in order to have that transmission of the disturbance throughout the system from one region to another, we have to have some way in order to do it. At least for a mechanical wave, we have to have some way to transmit that energy, transfer it from place to place, and we call that a medium. So every mechanical wave is associated with some material or some substance, which we call a medium. Some waves don't require a medium, and we won't cover those waves. Some examples of them are electromagnetic waves, radio waves, and light waves. We won't cover those, but you will see them once you get into Physics 152. So the speed of the wave, how quickly that disturbance travels from one end to another, depends on the mechanical properties of the medium, right? If I have different mediums, let's say some mediums we have here are air, water, rope, a string, wire. We could have oil, we could have some sort of molasses, but if we have a transmission of energy from one point to another, then how quickly that is transmitted depends on what the properties are that are transmitting it, right? What the mechanical properties of that thing that it's being transmitted through are, if that makes sense. So the speed of the wave, if we have different materials, it'll travel much faster than other materials. Think of if you were trying to speak underwater. You can talk very easily in the air, and your sound waves travel very easily in the air, but once you go underwater, the mechanical properties of water are much different than that of air, and so it's much harder to speak underwater, or at least to hear anything underwater. So it's really important to understand what a wave is and how it acts, and that we have a bunch of different particles. In that medium, you have a string of particles all touching each other, right? And they're all connected, right? There's molecular forces, atomic level forces, keeping it all connected. And the wave is actually just a series of displacements that the individual particles undergo when the particles experience a force. And these particles act more or less independently, and then they transmit their force to the adjacent particle. So as the wave propagates along, the particles are disturbed, right? And they move after they're disturbed, some force, right? And they have some mass, they're accelerated a little bit. The particles are disturbed, and then they return to their equilibrium after they transmit their force to the adjacent particle, or actually they're sort of transmitting their force to the adjacent particle while returning to equilibrium would be a more precise way to say that. But you have essentially basically what we have here. We have this particle moving up and down right here, and the wave is coming through. Maybe this is a little bit too fast, but the wave is coming through here, and this particle is just simply moving up and down, up and down. So it's feeling some force that's raising it, then it's being restored to equilibrium, and then it's feeling a force that's lowering it, etc. Right? So the wave is just a series of displacements. If I were to put a whole bunch of other little blue dots right next to this, they would all be doing the same thing, except they would be slightly out of rhythm with this blue dot, right? You have one out here that it's a bottom, top, and bottom, and the top, and so it's out of rhythm with this one, because this one is being forced by the wave to the left of it, and then, or to the particle to the left, forces this one up and then down, and then it moves, and then it forces the particle to its right, up and down, etc. Right? So it's forced by the particle on the left, and then it forces the particle on the right. If I had a lot of these in 2 dimensions here, like we have this wave down here, you'd see a wave traveling across. We have a lot of these particles are being displaced up and down, and that's all the way along here. This is like an ocean wavefront or something. You have a lot of particles are moving at the same time, but each one, moves in that same rhythm that we just saw on the previous, right? This one right here. So these move up and down. That's the same thing that's going on here. So we're looking at a bird's eye view, and we have a lot of particles out here moving like that. So important takeaway from that is that waves don't transport matter from one region to another. They only transmit energy. Okay, so they're not actually moving anything. If I have a wave start on one side of a lake, that doesn't mean that all the water on that side of the lake is moving to the other side. Actually, none of it is, right? The only thing that does travel through the wave is the pattern of the disturbance itself. So the pattern is the same for every particle moving down along the wave. Okay, so it only transmits energy, doesn't transmit matter, and what we see is actually a wave pattern. We see a pattern of the individual particles, but the particles themselves are not moving side to side, only up and down. Okay, let's look at the types of waves that we're going to talk about throughout this chapter now. So first off, we have some transverse waves. So transverse waves are waves that we see in this first, the waves on a rope right here are transverse waves. A transverse wave is described by, or it's a wave created when the force or the disturbance is perpendicular to the medium. So we have here a transverse wave is created by someone lifting up and down on this rope in order to create a wave that's going to sort of propagate along like that, right? So we have this propagation of it over here. It's actually, you see that, you see this already, the form here is actually the same form that's here, right? And then this part is actually when the wave is bringing itself back into equilibrium, is this part of the wave right here. So he lifts up on the wave right here. This is where you get your wave front, and this is actually the effects of gravity here, actually pulling the wave back down on itself. But we'll get into the details of that later. But a transverse wave is a wave disturbance that's perpendicular to the direction of the propagation, or perpendicular to the medium that it's traveling through. A longitudinal wave is sort of along the disturbance, right? So this is when the wave disturbance is parallel to the direction of propagation. So a longitudinal wave we have down here in this in these tubes here, and these tubes they have a top on them, and they have a bottom as well, so they're cylinders, and there's a plunger in here that's giving some force, and so this is our disturbance, so it's increasing a velocity in this direction, right? And so the disturbance is along the direction of the propagation. The particles in the fluid will move forward, and then they'll move back, and what we'll get here is we'll get a pressure difference between them when you have a sort of a pulse sending some force down, and it compresses the fluid inside, and then when it moves back, when I move the plunger back the other direction, it would decompress the fluid, and it would actually create less pressure, right? So we have this pressure difference where you can see the darker areas are higher pressure and the lighter areas are less pressure. So let me say that the equilibrium position, there's always going to be this equilibrium position that a wave is a disturbance from that equilibrium, right? So equilibrium for a transverse wave on a rope here would be when the rope is stretched tight. That would be when it's in its equilibrium position. Of course, that's only if we neglect the effects of gravity and the sag in it. In reality, with gravity, we'd have some sag in it there, and that might be its equilibrium position. And then finally, we have water waves, which is really, we'll just call them water waves. They don't really have much of a name other than that. Well, in general, they don't have another name. But what a water wave is a very complex mixture of both a transverse wave as well as a longitudinal wave. So take both of these together, which we have some perpendicular motion as well as some parallel motion, and we get ourselves a water wave that you see in the ocean at the beach. The equilibrium position for a water wave would be when the water is flat, or the water surface is flat. So along here, this is still in equilibrium, but here's our disturbance. The effect of this is sort of, remember I talked about the guy lifted it with his hand here and then gravity pulled it back down. Well, it's sort of the same thing here, where you're pushing forward, so we have this portion of the wave moving forward, but we're also sort of lifting up, and gravity is pulling it down, which creates this forward and down motion, right? So we have a forward and down motion, and of course, once that comes down, it's going to create a backwards and up motion as well. So we actually get this circular motion for water waves. If you've ever studied water waves before, you know that they move sort of in this circular pattern, and they move along like this. This is why actually it's due to that circular pattern that things on the surface of the ocean will actually move forward a little bit. The wave itself isn't really moving, but things are being thrust forward because of this complex mixture of both the transverse and longitudinal waves. We're not going to talk about water waves a whole lot. That's you can get a degree in that. So we're not going to go into a whole lot of detail on that, but we'll go into more detail just on transverse and longitudinal. And actually, we'll spend much more time on transverse waves than we even will longitudinal waves for this class. Okay, so now let's make it a wave and kind of talk about some of the characteristics it has. So if we were to take this this oscillator over here, this spring with the little thing attached to the rope here, and we oscillate it up and down in what we call simple harmonic motion, or SHM, simple harmonic motion, which is one of those things we actually sort of cut out of chapter 11, but we'll cover kind of the important parts of it in chapter 12 here. But basically, simple harmonic motion means that we have this amplitude reaches some maximum. These are the amplitudes here, and it kind of reaches these maximum points sort of like a constant over time. It's just bobbing up and down at constant amplitudes each time. So what it does is it creates, if we translate simple harmonic motion to a line here, what it does is it makes a sine wave. So that's the important takeaway as far as waves go for simple harmonic motion, is that we get a sine wave out of it. So we have this thing going up and down in simple harmonic motion, so it creates a sine wave here, or we'll say it's sinusoidal. Just means sine-like. It makes the shape of a sine wave. And then we have here some of the definitions. The very top part of a wave is its crest. The very bottom part of a wave is its trough. The distance from equilibrium to the very top or to the very bottom is known as the amplitude, and we represent that with A. So that's our amplitude. It's like the height. The maximum height of it would actually be twice the amplitude, right? Here we'd have an A here, and we'd also have an A here, right? So the very kind of maximum height, if we were down here on the bottom looking up, would be twice the amplitude. But we define amplitude as a distance from equilibrium position. The rope here, so we create this disturbance and it moves along like this, and we're not seeing, remember, we're not seeing a particle move along, because that wouldn't make any sense. The rope doesn't actually move along here. It's just the wave form moves along, right? So really, we just have some particle here moving up and down, particle here moving up and down, etc. And then this rope is restored back to its natural position by the tension in the rope. And actually, gravity and weight would come into play a role as well. But for now, we'll just neglect gravity and the weight of the rope, and we'll just say that it's just the tension pulling it back to its equilibrium position, which would be right here, right? Where that's a horrible drawing. That's right there. That's its equilibrium position, and the tension will restore it back to that. So each particle, so if this moves in simple harmonic motion up and down, as to create a sine wave here, each one of these particles also have simple harmonic motion, this up and down, the same exact motion as this right here. This motion is simply being duplicated everywhere or replicated everywhere along the wave. So when we have this simple harmonic motion, this generates this sinusoidal or sine-shaped wave, and we have these properties on it. First, we have the amplitude A, which is the maximum displacement of a particle from equilibrium. That's our amplitude right here. The period is the time it takes for one complete cycle. So we say, from cycle to cycle, if we have a starting point here and it goes up and then back down and then on its way back up, this would be one complete cycle, right? Very much like you've seen in trig classes with sine waves. And then we have another cycle. This would go up and then down. We could actually say a cycle is from trough to trough, or we could say from crest to crest, or some arbitrary point at the very beginning here on its way up, like right here to right here, right? These are all cycles, right? So the period, or t, which is the same variable we used for period before, is the time it takes for one complete cycle, or we say the time is 2 pi over omega. Omega here is very similar to the omega we defined in chapter 9, which is the angular frequency. This is 2 pi, because it's 2 pi radians per one complete cycle, times the frequency of it. Or we have the period is 2 pi divided by omega, which is, you'll see, is the frequency. We get from there, the frequency is the number of cycles every second, right? So that's actually 1 over t. If I substitute this omega, 2 pi f, in here, I'd have 2 pi over 2 pi f, which would be 1 over f, which would be the period, or we can solve that algebraically for the frequency is 1 over the period. So it's just the number of cycles we have in 1 second. And the units for frequency is in hertz. It's cycles per second. So very related to the period. So just to sort of kind of put it all together here, if I were to take like a time-lapse snapshot of a traveling wave in which we have our time is at 0 right here, and then t is a period. So this is at 1/8 period. That second figure you see right here is at 1/8 t, so it's 1/8 of the cycle through. This would be a quarter of the way through, 3/8 of the way through. This is halfway through the cycle, and then we get all the way back down to where we're all the way through the cycle, right? So we have here at time 0, we have this, we have a trough, a crest, and then it comes back down to a trough. You'll see after one cycle we should have that entire thing duplicated because we've added one complete cycle to it. So here's trough, crest, trough. This is what we started with, and we added one cycle on here, right? We started at the top, on our way down, back to the top. Now we're on our way down again. We added one cycle over that time t, the period. So we can also define the wavelength in this in this figure is the distance between the two troughs, or the distance between two crests, or some arbitrary point, as we talked about before. So that's the length of the wave, when it's in the x direction. I think on the previous slide here we said that we had a distance between these. If this were in time, then that would be the period. If this were a time axis here, but if this is not a time axis but an x-axis, then this is the wavelength from here to here, trough to trough, or crest to crest. That's the wavelength. If this were a time axis, then we would say this is the period from here to here, or from here to here. That would be the period. We'll get into more detail on that later on as well. But back to this figure here, we have the wavelength is a distance between two crests or two troughs, and you can see in this figure that one period would add one entire wavelength to it, right? So we have over one period that corresponds with one wavelength. And you also see, importantly here, that this is a point on the wave, right? This is at the low point, the high point, and the low point again. And you can see as it moves through time, the place of this dot varies, but the dot itself doesn't move over in this direction, doesn't move in the x direction. It only moves in the y direction, right? So it's at the bottom and it slowly moves up, and finally halfway through the cycle, this is it, halfway through the cycle, it finds its way to the top, and then it starts to come back down, and then all the way through the cycle it's back at the bottom again. And you see that holds true for all of these dots. They're all in the same x position, and they're simply moving up and down like we saw before. So you have to be careful to distinguish between the motion of the waveform, which actually moves along the rope, and the motion of the particle, which simply moves up and down. So the waveform is moving along because the energy is being transmitted, but the particles, individual particles, are still moving up and down. The wavelength is the distance between two troughs or two peaks in the waveform. And we use this, introducing another Greek letter for you here. This is the Greek letter lambda, and that represents wavelength, which you've probably seen that in some of your chemistry classes if you've taken chemistry already. So very much as that last slide suggested, there is a relationship between the speed of the wave. When we talk about speed in this chapter, we're talking about wave speed actually. So the speed of the entire wave form as it moves along. So this is the wave speed, and then the period, the wavelength, and the frequency of a traverse wave. And remember, a traverse wave is one where the disturbance is perpendicular to the direction of propagation there. So the relationship between them, the wave speed, the rate at which the waveform travels along the medium, v is given as v is equal to lambda f, or this is the wavelength times the frequency, or it's the wavelength divided by the time it takes. So that's lambda over t. So it's the length over time, right? Is the velocity. So hopefully you're saying, oh, well, length over time, that makes sense because it's very similar to a very familiar relationship that speed is equal to a distance over a time. It's the wavelength divided by the time it takes to get there. So wave speed is the same thing. It's the wavelength divided by the time it takes to get there. Lambda over t. In a longitudinal wave, or a wave whose disturbance is parallel to the propagation, then that's what a longitudinal wave is, right? When the disturbance is parallel to the propagation. We would actually look at the expansion and compression of a gas in a tube to look at our wavelength and amplitude and wave speed there. And so basically, if we have this plunger, very much like we had in that figure before for longitudinal waves, We have this plunger which pushes on it and causes some compression and then moves backwards and causes some expansion, right? The wavelength there is defined as 2 points between the compression. This is higher density, right? We have, or higher pressure, I should say. This is higher pressure, the blue areas, and then lighter pressure in the white areas here, right? So this is low pressure and then versus the high pressure here. So a wavelength and a longitudinal wave is the distance between the high pressure points, between two high pressure points, or the distance between two low pressure points, or the distance between 2 points of equal pressure. The amplitude is, there's a slight oscillation of the particles, right, between the low and high pressure, and that would be our amplitude, or the pressure difference between the low and high pressure zones. That's our amplitude there. And the wave speed can be calculated in a very similar way. These are longitudinal waves, are the waves that we hear. So when we hear sound, they're actually these sort of pressure waves, the longitudinal waves that we hear. And when we hear them, the amplitude is what we perceive to be the loudness. So the bigger the difference between our high pressure and low pressure is the loudness, and then the frequency, how close together these high pressure and low pressure areas are, is the pitch. Okay, so amplitude translates to loudness, frequency translates to pitch. So when we talk about wave speed, what does the speed at which energy is transmitted through a medium depend on? And this is the same thing as the wave speed, right? Wave speed is the speed at which the energy is transmitted through some medium. So what sort of things does that depend on? Does it depend on our input energy? Does that matter? How much energy we put into it? Does that dictate how quickly the energy is transmitted? Does the frequency at which we input the energy, does that matter? Or does the amplitude matter for our wave speed, how quickly the energy is transmitted? And maybe pause it for a second. You guys can try to answer these questions. I'll come back to it. But your answer should be no, actually. Wave speed does not depend on the frequency or the amplitude that we impart on the wave. That doesn't dictate how quickly something moves along, right? Changing these will change the frequency, amplitude, and wavelength of the wave and how the wave form looks, but will not change the wave speed, how quickly that energy is transferred through the medium. So it's not dependent on our input energy, our frequency, or our amplitude. So what does it depend on then? We need to remember that a wave is a transfer of energy, right? And so for energy to be transferred, work has to be done, right? So this kind of comes back to what I was saying, that second slide there with the animation. So for a wave moving left to right, we'd say the left side does work on the right side in order to transfer energy. And then that's transferred to one particle. If you remember back to that animation I had before, we have one particle transmitted its energy to the next particle, which then transmitted to the next one. So for a wave moving left to right, the left is doing work on the particle, it's doing it on the right side, and then the energy is transferred. But we're talking about the wave speed, right? So we're not talking about just the transfer of energy per se, but we're talking about how quickly that energy is transferred, which would actually be the power, right? So the rate at which energy is transferred is the power. So we're really talking about the power. Wave speed is more or less the power. It's the rate of energy being transferred. So therefore, the wave speed depends on how quickly the rope, or whatever medium we have, we'll use a rope here, is restored to equilibrium, or how quickly it transfers all of its energy, to be more precise. So it has some energy going in. The sooner it can transfer all of its energy and get back to equilibrium, then the sooner that energy is transferred to the next one, right? And so that's what we'd say is the wave speed. So it depends on how quickly the rope returns to equilibrium is really what dictates the wave speed. So what factors dictate how quickly equilibrium is restored? Let's say we're talking about a rope that we're given a transverse wave to it. What factors would dictate how quickly the equilibrium is restored? So if we consider a wave moving on a rope, what are the restoring forces on the rope? Or more accurately, or maybe a better question I should say, is what forces exist to bring it back to the state it was in before it experienced a wave? That's what a restoring force is. So a restoring force is something that brings it back to the state it was in prior to experiencing the wave. So it brings it back to the previous state. It restores it back to where it was before. So that's what a restoring force is. So what are the restoring forces on a rope? Say we're considering a rope here. You might want to take a second, answer these, or try to answer this question, then come back to it. But for one, we have the tension. The force that holds the rope steady would be one of the restoring forces to bring it back to the state it was in before. And we have another one here. Everybody guess? Maybe gravity, or the weight of the rope, right? Or more specifically, the mass per unit length of the rope, right? If I have a longer rope, obviously it weighs more, but I don't care about the mass of the entire rope. I actually only care about kind of the mass of each individual particle. Or I could simply say the mass per length. We could look at particles in terms of the length of rope as well. So the tension plays a role in restoring the force back to equilibrium, as well as gravity. So how would you expect these forces to restore the shape of the rope? Would a greater tension help it restore it faster, or would it be slower? And what about a more massive rope? Would that make the restoring force faster or slower there? If there's more tension in the rope, we would say that the rope is more taut, it's tighter, and we would expect the restoring force to be greater, right? So then the rope would restore faster. If the more tension is on it, the tighter it is, so it has a greater restoring force. So we would expect it to return to equilibrium faster. And remember, wave speed was all about getting back to equilibrium. So if tension means we get it back to equilibrium faster, then the more tension, the faster the wave speed. So we would expect the wave speed to be faster if there's more tension. Okay? What about if the rope is more massive? Think about Newton's second law there. F equals ma. Force is mass times acceleration. Then if it's more massive, we would expect the acceleration of the rope back to its equilibrium position to be slower, right? The more massive it is, the slower its acceleration, right? Given that we have the same force. So if we have a more massive rope, we'd expect its return to equilibrium to be slower. So we would actually expect a more massive rope to have a slower wave speed, which probably, if you ever tried to put a wave in a big rope versus a wave in a guitar string, then I think that you'll see that the wave travels much faster in a guitar string than in a giant rope for tug of war. So if it's more massive, it gets more sluggish and doesn't move quite so quickly. So it's faster if we increase the tension. We are creating a greater force, and so it is restored faster. If it's more massive, then we're slowing down the acceleration, and so it is slower. So finally, we can actually just give you the equation here for the wave speed of a transverse wave, a wave in which the disruption was perpendicular to the propagation. Then the speed is the square root of ft over mu. So ft is the tension force, and mu is not the same mu that we used in chapter 5. Unfortunately, that was our coefficient of friction before. That is not what it is now. Mu has been redefined as the mass per unit length. Okay, so the mass of an entire rope divided by the length of the rope would give us mu. So the wave speed is the square root of the tension force divided by the unit mass of the rope or whatever medium we have. So we say that the wave speed is proportional to the square root of the tension and inversely proportional to the square root of the mass per unit length, which is more or less what we expect, or actually is exactly what we expect from the argument we just had. Wave speed increases with tension and it decreases with mass. Okay, so now we have the wave speed. Let's talk about how we can describe a wave mathematically. And a little bit ago, I was talking about if we had different plots here, or we have a different independent variable. If we have like x here and we have t here, we actually had different measures between our troughs. If we're plotting in x, then that's our wavelength. If we're plotting in time, then the distance between the troughs of the crest is the period, right? That's just what I was talking about a few slides ago, and just wanted to point that out there. But the emphasis here is that there's a couple different variables going on if I want to talk about the y coordinate of the position at some time, right? I need a couple pieces of information. I need to know which particle I'm talking about. I need to consider, the y position of the particle depends not only on which particle I am talking about. If I'm talking about, let's say, a particle that's right here, right at this crest right here, then I have some distance over here in x, right? But when am I talking about that? I also need to say, well, when do I care about what that one's doing? Because I know it's changing in time. This particle is oscillating up and down, right? If I look at it in time, well, it's over here, but I don't know, maybe at some point it's at the very bottom, and maybe a different point in time it's up here at the top, right? So there's a couple variables that I need to define here. So y is actually a function of time, right? As well as the y position of a particle depends not only on which particle I'm talking about and the x direction, but also talks about when, or also is a function of when I am talking about it. When do I want to know where it is? So if we were just to consider the first particle where x is equal to 0 right here, then we would know that it would just be a function of time and it would just oscillate like this, right? We could know where the y position is just by knowing the time. And we'd have this equation for a sinusoidal wave. So y would be the amplitude times the sine of the angular frequency times the time, or replacing the angular frequency with 2 pi times the wave frequency, we have the y position is the amplitude times the sine of 2 pi f time, and then all times the time. Okay, so this is only if we have the position at 0. This is only good if I'm talking about the particle that is located at a position of x is equal to 0. If I want to consider some position of x other than x equals 0, I need to use an equation that incorporates the wave speed as well as the time, because it incorporates, I mean, the position in x will depend on the wave speed as well, right? It takes some time to reach a position x. And so why we need this function, the y coordinate is a position of both the location as well as the time, and we have the y position is the amplitude times the sine of the angular frequency omega times the time we're considering minus the position we're interested in divided by the wave speed. Or we can say that it's the amplitude times the sine of 2 pi times the wave frequency times the time minus the position over wave speed. This is the only difference between these is that I've replaced omega here with the 2 pi times the wave frequency. Or we could describe the y position in terms of the period and the wavelength. So this would be the y position is equal to the amplitude times the sine of 2 pi, and then the frequency is absorbed into this. So we have the amplitude times the sine of 2 pi, then times the time, the time we're looking at divided by the period minus the x position over the wavelength here, and this gives us the y position in terms of the period and the wavelength. And all of these equations, t is the time that we're considering the particle, and x would be the x coordinate of the position. Okay, so now let's look at what happens when a wave or just a pulse of a wave, one kind of up of the wave or down, reaches some sort of boundary, maybe reaching a wall or something like that. So this scenario, we'll look at a pulse traveling on a rope or a string, and then it is attached to a wall at one end. And the way that this pulse acts once it reaches a boundary depends on the conditions, really. The boundary conditions is what we'll call them. So it depends on whether or not the wave or the medium is free to move at the boundary, or if it's confined and not allowed to move. Basically, it comes down to really just either a conservation of energy or Newton's third law, really. If we have the boundary in part A, or in figure A here, we have that the pulse ends or hits its boundary, and it's fixed at the boundary, right? So it's fixed down here, so it's not allowed to move. And then in B, we'll look at the wave being reflected from a free end, so that way when it comes in, then this is free to move up or down as it wants. So those are the two different scenarios we'll look at here. And basically we have If it's free to move, then, which we have in part B over here, then we have a conservation of energy. And so the reflected pulse will keep the same shape as the incoming pulse. Basically, what's going on is that we have our incoming wave right here on the free end. The wave or the pulse is coming in, and then it gets closer and closer, and then it gets there, and then finally, when it hits the free end, all that energy is transferred to kinetic energy first, and then finally gravitational potential energy right here, right? So all that energy is transferred into moving this ring up the pole here, up this frictionless pole, and then it naturally wants to go back down. There's nothing holding it up there. The wave has already transmitted all of its energy up, so there's no force, no energy holding it up there, so it'll slide back down, right? So here it is at the top, and then it starts sliding back down, and it creates the same pulse traveling back the other direction, right? So it's the same exact pulse that came in, it's just going on its way back out now. If we have a fixed end, then it really comes down to Newton's third law here. So if the end is confined here, the boundary condition does not allow the medium to move at the end, then what happens is that we have the wave is coming in, right? And then it's getting closer and closer, and then it gets here, and the rope exerts an upward force on the wall, right? So it's exerting some force upward, and we know from Newton's third law that there's an action-reaction pair here, right? So the rope exerts a force up on the wall, but it doesn't move the wall up. And then so the wall exerts a downward force of the same magnitude down on the rope. And so the pulse ends up becoming inverted, because now it's like we just swung the rope down right here. The wall swung it down with a reaction to its incoming force there, incoming energy. And so what we get is the same shape wave, same amplitude, same period, all that, but the wave is inverted from the original wave that was incoming. So two types of scenarios we have. We have if the end is free, if the boundary condition is a free end, so it's allowed to move, then we end up with the reflected wave, or the reflected pulse has the exact same shape as the incoming or the original pulse. If the medium is not free to end, or not free to move at the end point, so the boundary condition is fixed, then we get the same shape again, but it's inverted. So it's just the upside down of the incoming wave. So let's say we want to know what happens when we have both an original incoming pulse, and then we also have a reflected pulse moving back on the same string. So we have a couple different waves acting on the string, right? We can use the principle of superposition to determine what the combined wave is going to look like. So the principle of superposition, I'll just read this here. It says that whenever two or more waves overlap, the actual displacement of any point on the string, or any medium, but we'll use a string in this example, at any time is the vector sum of the displacements of the individual waves as if the other wave were not present. And by vector sum, I mean if it's above its equilibrium position, we'll call it positive. If it's below the equilibrium position, we'll call it negative. So essentially what this means is that waves add together to either form a larger amplitude. If they were both positive, they would form a larger amplitude, or if they were both negative, they'd form a larger amplitude, or they'll cancel each other out. So if one has a positive amplitude and one's above equilibrium position, one's below equilibrium position, then they would actually have a canceling effect, because one would be positive, one would be negative, we'd add them together and it would get smaller, right? Or we can have some combination in between, anywhere in between those. So the details of this are really a pretty complex function in time, because as we saw in the mathematical description of a wave, waves are dependent not only on where we're talking about the particle, but also at what time. So they can get to be very complex functions in time. But the principle of superposition just basically says that we can add them together. So we can add one wave right on top of another wave. So let's look at some of those. So let's say we are going to superposition two waves on top of each other, and they're inverted waves. So one has a positive amplitude, or I shouldn't say that. Amplitude is always positive, but one is above equilibrium position, one is below equilibrium position here. So we have this incoming wave. This one is coming in this way. This one that's above equilibrium. This one is coming in this way. That's below equilibrium. As they get closer, each wave continues to have its own shape here. And then when they get closer still, then they're basically on top of each other, right? So this is the shape that one would have on its own, the one that's moving to the left, and the one that's moving to the right would have this shape if it was on its own. But we add these together and we get this combined shape that looks something like this, and they nearly cancel out. It's almost just a flat line. So when the two waves cross each other, the amplitude looks very small because they're kind of canceling each other out. And so then they continue to move along. This wave moves to the left, this one moves to the right, and then they continue to have the same shape that they had before colliding, if you will. And so they continue to move along. But the point at which they collide, the amplitude is much less. So basically what we have is, you have each wave has an amplitude inverted with respect to each other. Remember, because we're talking about superpositioning two inverted waves. And then during the superposition, they're nearly canceled out because they get the amplitude becomes very small at that point. And then after the collision, the outgoing waves resemble those that came in, but the sign is inverted, right? So this is like if I were just to take this as my center line, I'm just looking at the right side here, then I have this one had a positive position above equilibrium here, and then on its way out had a negative position. It's really just this wave kind of coming through. The wave going to the right is still going to the right down here, but it looks like it got flipped there. Let's take a look at superpositioning of two identical waves. So let's say here we have two waves of equal amplitude. One is moving to the left here, and another one is moving to the right, and they get closer and closer together. This is the shape that each one would have on its own right here, and this is the combined shape. This brown line is the combined shape. And you see that as they get closer and closer, they still individually would have these shapes, but they are getting closer, so it's making a larger amplitude here. As the peaks of both of them get even closer still, then the amplitude becomes nearly double of what it was before. And then, of course, after the waves pass, they continue traveling in the same direction they were prior to colliding there. So basically we have each wave has the same amplitude. During the superpositioning, the amplitude would nearly be doubled at this point down here, and then after the collision, the outgoing wave just resembles the same wave that came in, just going the other direction. So now the superpositioning of waves allows us to look at a very special case of superpositioning when we have, let's say we have a string that's attached to some fixed end. Then when that original wave is combined with its reflected wave, it won't look like two waves traveling in opposite directions anymore, but it'll actually just appear as one wave that appears to be divided into segments. The reasoning for this is that there's some point at which the sum of the original and the reflective waves will always be equal to 0. Just like we were looking at a minute ago with the superposition of waves, let's say that there's a point in which they'll always sort of cancel out, and so the sum of them will always be equal to 0, and we'll call this point, there will be no vertical motion of the particle at that point, and we'll call that point a node. So a point that doesn't move in time is called a node. And the converse of that is that there's a point or points at which the original and reflected waves are both at their maximum amplitude, and that would be called an antinode. So we get the maximum displacement at those points. So you can kind of think back to what we were doing with the cancellation and the adding of, or the construction of waves with the superposition principle. If we have them, in the first case we had them canceling, and in the second case we had them adding. So we'll look at this kind of going on at the same time for some fixed wave. Let's show you some pictures here. So when the nodes and antinodes align, there's no destructive interference, which we'll talk about interference in a minute. And we have this steady state condition. Steady state meaning that it's constant in time. The state is steady, so the time doesn't play a role. It doesn't change at all over time. So steady state means that it's constant in time. And depending on the shape, size of the medium that transmits the wave, we can get different standing wave patterns established as a function of the energy in the wave. So we have here what's going on. We have a node right here. If we have a string that is a half wavelength long, then half of the wavelength is up right here, then it gets reflected, and then half of a wavelength here, reflected back again. And so we have two nodes right here. So there's a node at each end, and then we have an antinode in the middle here where we have our maximum displacement. If I have a string that's one entire wavelength long, then I start some disturbance down here at this end, and it comes up and then travels one complete wavelength, and then it hits a fixed end and it gets inverted, and so we have the other wave come back through like this, and they both cross through the 0 point kind of at the same time. And so there's a node right here as well as nodes at the end, and then two antinodes right here, kind of halfway between each of these nodes. Again, if we were to have a string that's 1.5 wavelengths long, you'd see it would continue to go. There's one wavelength, and then there's another half wavelength here, and then it's reflected back, one wavelength, and then another half wavelength there. And we have really the same positions at where it's crossing through the Y value at the same time. So in this case, we have 4 nodes and then 3 antinodes. Again, if we had something that was 2 wavelengths long, then it would just continue to be a full 2 wavelengths. There's one wavelength there, and then another wavelength here, and then it gets reflected back to be one wavelength, and then another wavelength right there. 2 wavelengths, and we end up with how many? 1, 2, 3, 4, 5 nodes, and 1, 2, 3, 4 antinodes here. So just a schematic over here of of a node and an antinode. We have the nodes are the point in which there is no vertical motion. These are the nodes represented by N. The string never moves here. And then we have the antinodes are halfway between these nodes, and they're represented by A. And so that's where the amplitude is the greatest for the string. An animation might help to kind of understand what's going on in time with these waves to see the nodes and antinodes. So let's see if we can get an animation going on here. Basically, we have this black line is the sum of the two waves, and let's see, this red line is a wave that's going in, and the blue line is the reflection of that wave, based off of what we went over before with Newton's third law and the action-reaction pair. This is a fixed end down here. So you can see that the sum of these at a node, the sum of these is always equal to 0. So we have the red line and blue line are out of phase here, and they're equidistant at all times from their equilibrium. So they're always, their sum, and one is above, one is below, and their sum will always be equal to 0 here. So that's what we define as a node, and we see that happening at every one of these nodes in which we have they both cross through 0, red becomes positive while the blue is negative, and then vice versa here, right? So that's what's going on at our nodes. And then at the antinodes, we have they both cross at their amplitudes cross at the same time. So they're both at a high point and they're both a low point, creating a large amplitude right here at the antinodes when the maximum crosses at the same time. So node is a point in which the two waves together combine to produce no vertical motion, and then an antinode is where they combine to produce maximum vertical motion between the two. Now we can also extend this to standing waves in 3 dimensions as well. We won't cover this a whole lot mathematically, but I think it's very interesting. It can make some cool graphics with it anyway. So let's say we have just sort of one antinode. We would get something here that's just oscillating up and down. It doesn't even hardly look like a wave. There's just one antinode right here in 3 dimensions. We can also extend it so we can put a couple cross-modal lines in here. We get 4 antinodes, and we have antinodes here and here, and we have here and here, and we have a node right here at the center, as well as kind of nodes at these edges here. But antinode right here, and nodes, I guess, in each of these quadrants, if you will. So you can just kind of zone out on this for a little bit. So standing waves, unlike traveling waves that move along the medium or the rope, do not transfer energy from one end to another because they're standing there stationary. There is some local transfer of energy kind of between like the node and the antinode, but the net transfer of energy from one end to another is 0. So yeah, they don't transfer energy from one end to another. And the distance, as you probably noticed in the past in those pictures and animations, the distance between successive nodes or antinodes is a half of a wavelength. So 1/2 of lambda, or lambda over 2. So since the standing waves depend on reflected wave, the reflected wave being in the same place as the original wave, we have to have a specific length of the medium that can produce a standing wave. So it's dependent on how long that medium is, or how long that string is, say if we're using a string. And so the length of the string must be some number n, which is an integer, times lambda over 2, because we have the distance between the successive nodes or antinodes is half the wavelength. So this is our distance right here. So the length of the rope must be some integer multiple of this value of lambda over 2. So L represents the length of our medium. We'll say the length of the string. N is any integer, 1, 2, 3, 4, 5, 6, etc., times 1/2 of the wavelength that our wave has. So then we can use that to express also the wavelength and the frequency of a standing wave in terms of the length of the medium, L. So say here the wavelength, we can have different wavelengths with different frequencies as well, right? So different n values. So we can have a first wavelength would be equal to 2L over 1. Our second wavelength we can have would be 2L over 2, or just L, right? So it can be the length of the medium itself. So we can have sort of, if you look back to that figure where we had the string was half a wavelength long, or it was 1 wavelength long, or 2 wavelengths long, or 1.5 wavelengths long, etc. This is how we can determine the wavelength from the length of the medium here. Basically, we can have a lot of different wavelengths, and so our first wavelength would be 2L over 1, second wavelength 2L over 2, or just the length of the medium itself, and then etc. We can have any integer value of n. And the same goes for the frequency. The frequency of the first one, the first frequency would be just 1 times the wave speed divided by twice the length, and this is actually, we'll call this is the fundamental frequency. Actually, F1 is the first frequency it can have. We call this the fundamental frequency of that particular string or that particular wave, and then we can have other frequencies on top of that. So say F3 would be 3 times the wave speed divided by twice the length, and that would be the n times the third frequency, right? So this is, or actually not n times the third frequency, it's just 3 times the fundamental frequency. So the frequency, like the third frequency here, would be 3 times the fundamental frequency. So if I give you the fundamental frequency and then ask you for what the third frequency is, you can just multiply the fundamental frequency by 3. But this is how we can get wavelength and frequency depending on the length of the medium for a standing wave. So this idea of the frequencies, the fundamental frequency of a standing wave, is very important in music and musical tones, and just sort of a graphical representation of what I was just saying with the equations. We have here our fundamental frequency is the frequency, this is the smallest frequency, and it corresponds to the longest wavelength, right? So if I have here the longest wavelength, so if my wavelength over 2 is equal to L, then this will give me my smallest frequency, and this is what we call the fundamental frequency, in which half the wavelength is taken up in the entire length of the medium here, and then obviously then the wave reflects back, and we have the other half of the wavelength on the way back. This is the first picture we saw when we first introduced standing waves. So we call this the fundamental frequency when n is equal to 1, and it's the shortest frequency and the longest wavelength that we can have for a standing wave. The second frequency, n equals to 2, we'll see the equation down here for the length related to the wavelength, or the length of the medium, L, related to the wavelength, lambda. And we call this the second harmonic. The fundamental frequency is the first harmonic. Second harmonic is the second frequency. We also call this the first overtone. It's the first tone over the fundamental tone that we have. Again, this is very relevant to music and whatnot, musical notes. The third harmonic would be the second overtone, or that's when n is equal to 3. So we have essentially 3 standing waves in here, right? Second harmonic, we had 2 standing waves over the length. The third harmonic, we have 3 standing waves. The fourth harmonic, we'd have 4 standing waves over the length of it, right? So here's our 4 waves here. And we call that the third overtone. If we combine this with our previous equation for wave speed, then we can get the fundamental frequency for a vibrating string, because we had wave speed in our equation for the fundamental frequency before, and we get the fundamental frequency for a vibrating string when we have standing waves is 1 over twice the length of the medium, or twice the length of the string, times the square root of the tension force divided by the mass per unit length. And this is just how we defined wave speed before. This whole thing right here is the wave speed V. So that's how we can get the fundamental frequency based off the length, the tension, and mass per unit length. It's the fundamental frequency of a standing wave. So the standing waves that we were talking about are an example of wave interference, in which 2 waves interfere with each other in order to form a new wave. Not really any new concept here. It's just sort of putting some labels on some things that we've actually already discussed in our discussion of standing waves. So we have a couple different types of wave interference. First, we have constructive interference, in which the wave is constructed to be larger. So we have the high point of one wave corresponds to the high point of another wave. That would be constructive interference. This is where we get our antinodes in a standing wave. The result is then a higher amplitude wave between the two. We also have destructive interference. So this would be where the high point of one wave corresponds with a low point of another wave. And again, this is where we get the nodes in standing waves. And so the result here is a cancellation of the two amplitudes. So constructive interference builds together. All we're using is the principle of superpositioning here. So we add the two waves together. If the two high points correspond, we get a higher amplitude wave. If a high point corresponds with a low point, then we get a cancellation of the two amplitudes. So I have another little animation here to show constructive and destructive interference. We'll say this black line is the sum, the vector sum of the two waves, and just for simplicity, we'll say this sort of greenish yellow line is just stationary, and so we have another wave moving on top of it. So as we have this blue line is on top of the green line, then we have constructive. When they cancel out, it's destructive. So we have here, they're in line, constructive, and then they're out of line or out of phase. We'll call them 180 degrees out of phase, since there's 360 degrees in one complete cycle for a sinusoidal wave. Then if they're completely out of phase, we have destructive interference. If they're in phase, so their amplitudes line up, we have constructive. So we have here destructive, and then we have here constructive. Again, destructive interference, the amplitudes cancel, amplitudes add here for constructive interference. Okay, so that's wave interference, and that's destructive and constructive wave interference. So let's talk briefly about the waves that we hear, or the sound waves. And I said previously that a wave we hear, a sound wave, is a longitudinal wave, which is created by a pressure disturbance, right? That was the one which we had a plunger and a tube, and we were pushing it back and forth to increase and decrease the pressure. So a sound wave is really interpreted in terms of a variation in pressure. Imagine putting your ear at the end of that tube, you would hear some pulses in your ear. And so, I mean, I'm not going to go into the biology of it a lot, but basically we have some pressure fluctuates above and below atmospheric pressure. That's where we get our pressure disturbances. Then these pressure disturbances are kind of channeled by the auditory canal here. So we have our pressure disturbances. So we have some region of high pressure here that comes in. This is high pressure, and then there's a low pressure behind it, and then some more high pressure, and this goes into the auditory canal, and then it vibrates your eardrum. So some rattling in here, which then rattles these three bones, the incus, malleus, and the stapes, and it, I might not have pronounced those right, but it vibrates these three bones, and then it's eventually just transmitted into nerve impulses and sent to the brain in order to interpret them as sound. So the intensity that we hear from those waves coming in is given to us as I. I represents our intensity. And so these sound waves, they transmit energy, just like any other wave. It transmits energy from one region to another. And the intensity is the rate at which that energy is transported by the wave per unit area. We say the intensity is per area across some surface perpendicular to the direction of propagation. Essentially, since we're talking about it being it's the time average rate at which energy is transported, then we said the rate of energy change is power, right? So essentially, sound intensity is just the power transported per unit area. We divide it by some area to talk about our intensity. And so the average power emitted by a person speaking just in a regular conversation, just to give you guys a little frame of reference here, is roughly 10 to the negative fifth watts. That's the average power emitted by a person speaking. The smallest sound a person can hear is roughly 10 to the negative 12th watts per square meter. This is just laboratory testing to get that, and we use this when we're defining our intensity. We'll define that level as our reference intensity. So we'll call that I naught is our reference intensity level, which is equal to 10 to the negative 12th watts per square meter. So that's our reference intensity when we define a sound level. So when we define the sound level or intensity level, which we'll use the variable beta for in this, it's defined logarithmically. It's defined on a logarithmic scale. So beta is equal to 10 times dB. dB is decibels, so it's 10 decibels times the log, and this is the base 10 log. It's not the natural log, but it's base 10 log of whatever intensity we have for our sound over our reference intensity. So our reference intensity here is, like we said on the previous slide there, 10 to the negative 12th watts per meter squared.
So just to get an idea of sort of how loud something is in terms of decibels, if we had the log of 1, so if we have our intensity is the same as the reference intensity, which remember is the faintest sound that someone can hear, then we'd have the log of 1. If we have our intensity equal to the reference intensity, we'd have the log base 10 of 1, which is 0. And so we'd have 0 times 10 decibels. We'd have our sound level would be 0. That's the faintest we can possibly hear. If we had a sound level 10 times the reference intensity, so 10 times the most faint noise we can hear, then the log base 10 of 10 is equal to 1. So that'd be 1 times 10 decibels. That would be 10 decibels. So 10 decibels corresponds with a noise 10 times as loud as or 10 times as much energy, or 10 times as intense as the faintest noise we can hear. Let's say we had a noise that was 100 times the reference intensity. So our intensity is 100 times our reference intensity, or 100 times as much energy, or 100 times the intensity. Then we'd have log base 10 of 100, which is 2, times 10, which would be 20 decibels. So 20 decibels represents a intensity that is 100 times that of the smallest intensity we can have. So that's how the sound level works on a logarithmic scale. So it's really some multiple of the reference intensity here. So now imagine that we take two waves that we superimpose on top of each other, but each of these waves has a different frequency, so it's traveling a different distance in time, right? So there's a different frequency to it, and what would happen here is sometimes we would get some constructive interference, and then sometimes we would get destructive interference because they wouldn't be in sync anymore like we had standing waves. So the constructive interference would result in hearing a louder sound, right? Because this would increase the amplitude, so we'd hear a louder sound. And if we have destructive interference, this would result in having no sound whatsoever because the amplitude would be wiped out between the two. The louder sound that we get is called a beat. So when that louder sound comes through and we hear a beat. And so essentially, the beat we hear is the difference in the frequency of the two sound waves. So I'll put a figure up here on the next page to better explain this. But basically, we have two waves with different frequencies, and that results in sometimes constructive interference, sometimes destructive interference. And what results is hearing a sound sometimes, and what we hear sometimes is called a beat, and that frequency is a difference in the frequencies of those two individual waves. So let's say we have two tuning forks that we ring, and we have two slightly different frequencies of each tuning fork. So we have one tuning fork here is this red line, and another tuning fork here is this blue line. So the red line moves along, like this, and the blue line is moving along, and they are out of phase, completely out of phase right here. So when they add up, then it becomes a zero net displacement here. And then once they get over here, they're perfectly in line, right? They're actually perfectly lined up right here, pretty well lined up here and here. And we see that we have our sort of maximum, our amplitude is maximum for the two waves right here because they're added together, right? so this continues along, and they're in phase right here, and then they go out of phase again right here. And so we have our frequency, our actually the amplitude that we hear is destructive interference, and so there's very little amplitude right here, and then again they get back together, and the beat or the amplitude is large again. So the beat we hear is basically the time between these dead spots in which the amplitudes were canceled, and so the beat sort of ramps up and then hits its maximum, and then it ramps down again. So the beat here is the time, or this period in which we're hearing some sound, and the beat is the loudest, or actually the whole thing here, but the beat is the loudest where the two waves coincide. So they interfere constructively when they're in step or in the same cycle, and they interfere destructively when they're a half cycle out of step or out of phase, let's say. So I have a little animation for this as well that basically will just show this animation on the next page will show kind of both these, the red and the blue, moving at the same time, and so we'll get the beat frequency will be being built and then deconstructed as we go along. But let's take a look at that. So we have here, actually I think I said the red and green would move at the same time, but we'll leave the red stationary just to make it a little bit easier on you. So we just have another frequency kind of moving on top of it because the frequencies are out of line. So as they add together when they're in line, so let's just follow this one right here. They're out of phase and it gets really small. They're in phase, so it's very big, and then it goes to be out of phase again, and so it's getting very small again, and then it picks back up. So follow it again here, out of phase, and then we have them in phase, we have a peak, and then out of phase again, going back down to 0, and then right back up. So it's just going, our amplitude is changing over time, in which we have a large amplitude and then no amplitude, and then it keeps changing over and over. So this is our beat, is between, get this going again, this distance between these two lulls is our beat over here. So this distance right here is our beat. The beat frequency is given as the difference of the two frequencies of the sound waves. So really we can get the frequency of the beat that we hear is just take one frequency and then subtract the other frequency, and we have the beat frequency. So F1, the frequency of wave 1 minus F2, which is the frequency of wave 2. So that's how we get beats and a beat frequency. So the last thing we'll talk about in this chapter is the Doppler effect. So instead of what we did with beats and the beat frequency, instead of superimposing one sound wave on top of another sound wave with different frequencies, let's say that we can change the frequency by having a sound wave coming from a source, and then we're moving towards it. So we have down here we get the dude with the boombox and a skateboard, and then he's walking towards the cop, or the cop is actually he's standing still, and the cop is walking towards him. And so this will effectively change the frequency that the cop hears, right? The wave is moving this direction, but he is moving this direction. It's like having a change in the frequency and the sound that the cop hears, right? And so let me denote these here. This S will denote source, and this L will denote listener. So we have the source and the listener here we'll use in our equations. But the effect of moving towards it would change the frequency in which we hear the sound. The faster we move towards it, the more we change the frequency, right? And so that's the effect here, sort of similar to beats. We can also have a situation in which the skater is walking away from the cop, and the cop is walking away from the skater, or vice versa, they're walking towards each other. They can both be moving. We can analyze both of those, and we won't go through the whole derivation of it, as this video has gotten pretty long already. But if we assume that there's no wind, which is a pretty key assumption here, because a wind would carry the sound, it would change the frequency. Then in that case, we have the medium itself is moving, so then the wave in the medium is moving. It makes much more complicated. So we'll definitely assume there's no wind. Then we'd have a listener moving toward a source would hear a higher pitch, which would be a greater frequency. That's why we would hear a higher pitch. And a listener moving away would hear, we would have a less frequency, so we would hear a lower pitch, right? So in general, we have this equation that the frequency of the listener hears, so this is the frequency that the listener hears, and this is equal to the wave speed plus the velocity or the speed of the listener divided by the wave speed plus the speed of the source times the frequency at the source. So really this is the frequency the listener hears is the same as the frequency of the source, but then it's modified somehow based off of the movement by the listener and or the source. So like I said on the previous slide there, L denotes the listener who's hearing it, S denotes the source where it's coming from, and V is the speed of sound through the medium, which can vary from medium to medium, but for the most part we will use air if we're talking about listening to something. So this can be used if both the listener and the source are moving, or one is moving and not the other, but we have to choose the signs accordingly. If the listener is moving to the right, we'll call it a positive velocity. If the source is moving to the right, we'll call that a positive velocity as well. And if they're moving to the left, then they would be negative quantities. The speed of sound, however, V is always positive. So that will always be a positive value. We'll never have a negative value. We don't need to say, oh, well, the person is to the left of them, so the speed of sound needs to be negative. That's not the case. The speed of sound is always positive. The only things we need to worry about changing signs are the speed of the listener, the velocity of the listener, and the velocity of the source. We can also use the Doppler effect to measure the distance and movement of stars and galaxies by using a Doppler shift for the speed of light instead of for the speed of sound. So in this case, we have the frequency that the listener hears, or in our case, we're the observers, we're the listeners, right? So the frequency we hear is equal to the square root of c minus v, the velocity of the object, divided by c plus v. V is the velocity of the object here, still that's moving the star or the galaxy or whatever. And c is the speed of light, which is almost 3 times 10 to the 8th meters per second, and then times the frequency of the source. This is where we get the term red shift, you might have heard before, because the Doppler shift is kind of almost always in the longer wavelength, or towards the red end of the light spectrum. And so generally we get the shift as a red color. So red shift actually refers to the Doppler shift in determining the distance and movement of stars and galaxies using the Doppler effect. Another way in which the Doppler effect is used is actually the radar guns that police use also employs the Doppler effect. They essentially send a radio wave to a car, and then the car will act as a source, and they're sending constant radio waves to it, and then they measure the different frequencies sent back, and they get a beat frequency that's sent back, and then from there they can calculate, or the radar gun itself can calculate the speed at which the car is moving. So I know this was a pretty long video, a lot of material in chapter 12, but we'll work out plenty of examples in class. But that does it for chapter 12 and everything you'll need to know about waves, at least in this course. Thanks for tuning in. Okay.